Okay. The course is called Introduction to Cluster Algebras and Cluster Varieties. And if you look carefully, you realize that there is no definition of the cluster algebra yet. There are some cluster structures and some sorts of definition of cluster varieties, but no algebras, which are first keyword in the title. We are somehow in the middle of the course. Maybe it's time to fill this gap. And I'm going to do this, but on the second slide. But first, I will try to recall you something which I believe many of you already heard. No notion of the Newton wrote polygon, but actually polytope. Okay, by color. This is some analog of the notion of the degree of the polynomial, but for the case of polynomial of many variables. Okay, definition. Let's take any polynomial, which is a Laurent polynomial. Okay, ring coefficients not important. Let me write z on some variables. Let me note them by x. So one can write that P is the sum of M, which belongs to Gn, some coefficient Gn times the monomial x1 power m1 and so on, xn power mn. Newton polytope of P is a convex of points M in the M inside the real space, points such that the corresponding coefficient is non-zero. Maybe I have to write the simplest example. So if polynomial P is equal to something like x1 plus x1 inverse plus x2 plus some coefficient cx2 inverse, then then we have 4 points, 4 m's for which coefficient is non-zero. So the 1 0 minus 1 0 0 1 and 0 minus 1, and the corresponding Newton polytope will be polygon with these vertices. Maybe I should. Okay, like this. If this is a polynomial on one variable, then the Newton polytope is a segment, but it's easy. It's easy notation. Okay, we will need this notion such we talk a lot about Laurent polynomials. There are clear properties of this notion, which I state. So let PQ be two Laurent polynomials. First, Newton polygon of the product is the Minkowski sum. of the Newton polytopes of the summands. By definition, okay, maybe here I'll write in words. By definition, the Minkowski sum is just a set of sums of vectors such that x belongs to one Newton polytop and one belongs to another Newton polytop. This is some sort of the statement for polynomials on one variable. This is some sort of statement that degree of the product of two polynomials is equal to sum of the degrees. And the second property is Newton polytop of a sum of two polynomials belongs to convex whole of Newton polygons of P and Q. And there's a particular case which is important for us. If P and Q doesn't have minuses, subtraction free, then Newton polytop of the sum is equal to convex whole of Okay, any questions? Okay. Now let's go to the definition of the cluster algebras. Let's fix some seed. And today we'll talk only about A cluster structures. So seeds as our first definition. We have some antisymmetric matrix B and set of variables A1 labeled by A's, which correspond to the vertices of the quiver. In principle, some of the vertices can be frozen, so corresponding variables are called frozen variables. It is possible. Okay, definition. Cluster algebra for CT. I apologize for the confusion of notation. So capital A stands or sometimes will stand for variables, sometimes will stand for algebra. I will try to use different fonts for this. So Pascal A for algebra and just A for variables, but probably the confusion is unavoidable. IT is this subalgebra in algebra of rational functions of maybe since we have Laurent phenomena, I just write for simplicity that algebra of Laurent polynomials with the initial cluster algebras, initial cluster variables generated by A prime. Okay, maybe in words, generated by cluster variables in all seeds T prime connected to T. By mutations. By Laurent phenomena, we know that all cluster variables which can be obtained of this sequence of mutations are Laurent polynomials in original cluster variables with integer coefficients. So all A prime all actually belongs to this algebra, and then this generate, in generally speaking, some subalgebra. And this is algebra is called cluster. There is a related definition which we will actually use today, which is the title of today's lecture is not cluster algebra, but upper cluster algebra. Now let me define what is it. A upper bar T maybe I should write word cluster algebra somewhere. Okay. Okay, and now I'm defining the upper cluster algebra. This is some this is I can define right the formula. This intersection of z of a prime 1 plus minus 1 a n prime 1 plus minus 1 intersection given by t prime where t prime, which consists of b prime and a prime, is a seed connected to T. So we take all seeds which are connected to our initial seed by sequence of mutation and take Laurent polynomials with the corresponding cluster variables. Again, by how to say, so there is a how to say it? So there is a following property that A of t is a algebra of A bar of t. Indeed, any cluster variable is belongs to this intersection because any cluster variable is Laurent phenomenon in any cluster variable in one seed is Laurent polynomial in cluster variables in any other seed. So this is why this is called upper cluster. Well, this is some sort of upper bound. Another, maybe I should put it as a remark. Okay, so this is remark A, and remark B said that actually this A bar of T is a more natural object from geometric point of view. This algebra of regular functions on a cluster variety. Indeed, let me recall that for any seed, we can construct the torus, and A's are coordinates on them. And the A cluster variety is obtained as a glue. The definition of cluster variety is obtained by gluing all these torus using all such tori using notation. Regular function in each tori are just Laurent polynomials. So the regular function on the whole cluster variety are some functions which are regular on each chart. So the intersection. In this definition, I consider a cluster variety as a scheme of a Z. One can, if you don't like Z, you can write here complex numbers and here complex numbers. I ignore such difficulty. So this definition may be more natural from the algebraic point of view, but this is more natural from the geometric point of view. I should say from the very beginning that quite usually this algebras are isomorphic. There are some criteria for this and so on, but there are also examples where they are not, and these examples include important examples, not just some monsters, but examples which appear in this application. Okay. These are the general definitions, and now I'm going to give one more definition, which looks rather technical, but it appears that appears to be very useful. So let me define that U of T. U stands for upper. So this is some simplification, some version of the upper cluster algebra. Okay, so U of T is a Z of A1 AN plus minus 1 intersect with big intersection for J from 1 to N. Or maybe not N if we have less vertices which mutate. Let me look which notation I prefer for this stuff. Sorry, maybe not here. Maybe here. Okay. Okay, here maybe I should write M. If you have frozen variables, then here I should add them without negative powers. Okay, the U of T is intersection of the Laurent polynomials on the initial seed. And Laurent polynomials where one of the variables, say g, is replaced by their mutation. So you see here, I take intersection of the Laurent polynomials for all seeds which are obtained from T by any sequence of mutations. And here I take intersection only for the seeds which are just adjacent to T. Maybe I need some space. Let me bring it this way. Okay, now this formula looks better. At least I hope so. So here we have T, and by G it is adjacent to some Tj. And Tj cluster varieties for Tj are A1, Aj minus 1, and then J's variable is replaced by Aj prime. Okay, is this definition clear?
I think yes.
And now the main theorem, which states the following: if seeds T and D prime are co-prime, then these algebras are isomorphic. And maybe before the theorem, I should give a definition. Sorry. I mean, if we have seed, so let's take some seed T, which consists of then this seed is supplied by sequence of mutation operations. Ag prime times Eg is equal to some polynomial p, which is sum of some monomials, pg. Seed is called coprime if all these polynomials are coprime. Maybe you remember, but I recall it. What is PG? PG is the sum over Bij greater than I, AI in power Bij, or sum over Bij less than I, AI in power Bij. So each PG in our case is a binomial sum of the monomials, and seed is coprime if all those binomials are coprime. This is rather mild conditions. Quite usually, this is true, and I'll going to convince you. And now the theorem says that if this mild condition is satisfied, then this algebra U doesn't change under mutation. So here I assume that T and T prime are related by some mutation. And corollary, which I'm going to state in a minute, but it means that if all seeds are coprime, then this algebras U are the same, and this U is just coincide with upper cluster algebra. So we can compute upper cluster algebra somehow, which is defined globally. We take some seed, we do any number of mutations, but this global thing can be computed locally. Just we take one seed, its neighbors. Okay. Let me explain why this condition is very mild. So this is the following lemma. Seed is not coprime if and only if there are two indices I1 and I2, so two rows, such that the corresponding rows are proportional. And this coefficient of proportionality is given by the rational number, which is odd. So it has odd numerator and denominator. Proof. Okay, this direction, what does it mean? It means that we have two polynomials, I1, and from this condition, it follows that this polynomial can be written as some monomials in power A2 plus some another monomials plus another monomials also in power A2. And corresponding polynomials for I2 have this form. So I assume for simplicity that A1 and A2 are coprime. Then from this condition follows that any B that A2 is a divisor of any BI1G, and A1 is a divisor of any BI2G, and if we divide, we get what's given by M1 and 2. Okay, now as we see, A1 and 2 are odd. So M1, we have common factors, both P1, PI1, and PI2. So M1 plus M2 is a factor of PI1, and M1 plus M2 is a factor of PI2. So C does not comply. Okay. Now let's consider the opposite direction. Assume that C does not comply. Then there are two pi1 and pi2 which are not complying. But note that these two polynomials are actually monomials. So their Newton polygons are actually binomials. It has sum of two monomials. So their Newton polygons are segments. So hence Newton polygon of pi1 and Newton polygon of I2 are segments. And any factor of the Newton polynomial of the polynomial such that it's Newton polynomial. And now I'm going to say that this segment should be parallel. Parallel segments. Because we have two segments and any factor. So if we have some q which is divisor of pi1, q is divisor of pi2, then Newton polynomial of q is also should be also segment because Newton how to say the Newton polytop of the q times something is an Minkowski sum of Newton polytop of q, Newton polynomial of this something. And if the sum is a segment, that each segment is a segment. And this segment should be parallel of this pi1 and pi2. Okay. So they are parallel, and hence we can write that pi1 is some maybe yes L in power A plus M in power A, and pi2 is some L in power B plus M in power B. So it remains to state that these two polynomials have common divisor only if A and B are both odd. This is now the statement of the polynomials in one variables. So since maybe instead of B I use index. So here T2, here T1. Since T in power A1 plus 1 not prime if and only if the indices A1 and A2 are odd, we are done. Okay, so maybe details are not well organized, but I hope the idea of the proof is clear. There is a very clear corollary that if matrix adjacency matrix B has a full rank, then the seed is coprime. Indeed, by this lemma, if two seed is not coprime, only if it has two proportional rows, with also with some odd coefficient, but never mind. If matrix B has full rank, then there is no proportional rows, so the seed is coprime. Okay, but in order to apply this theorem, we have to know that both T and T prime are coprime. In order to apply this theorem many times, we need to know that all seeds which are obtained from this initial one are coprime. Okay, but there is a following lemma that run until the mutation, rank of the adjacency matrix remains the same. So if before I will go to maybe prove this lemma, but even before this, we have the following corollary. So if B has a full rank, then all matrices you obtain from B by mutation will have the full rank. So all seeds which you obtain from B will be coprime. So all U's will be, we can apply this theorem. So all U's will be isomorphic. Hence, upper cluster algebra will be isomorphic to this upper bound computed in one seed. So this is some sort of so we somehow describe some global things, the functions of the some variety, which conclude of infinitely many charts by the local data. We just glue the original chart and its neighbors. This some similar statement is called starfish lemma in the theory of cluster algebras. So, what exactly what is actually called starfish lemma, we'll discuss next time. So this is starfish because we have some star. It has its neighbors, and this the star of the in our is the quiver in the graph, which vertices are seeds and edges correspond mutation. Actually, star of one vertex describes the whole story. Okay, so this is what to remember. Proof of this lemma is straightforward. Its proof can go like this. So let's think about B. So consider this B as a matrix of the antisymmetric, as a Gram matrix of the antisymmetric form. On GM. Namely, we can define this form that pairing of EI and EJ is equal to BAJ. Then mutation B to B prime is actually equivalent to the following transformation of the basis. So we define new basis A prime G by the following formula. So the corresponding vector will be minus EI mutation. Let it be mutation vertex K minus so new basic vector minus EK if J is equal to K, EJ plus maximum if from BJK and 0, EJ, for J not equal to K. So this is some sort of triangular transformation. In this, I mean, something like reflection, and something reflection, something triangular transformation. If we take reflection with according to hyperplane, which are orthogonal to EK, then usually just some EK change the sign, and all other vectors changes by something which is proportional to EK. So here should be K. But in this cluster story, we have some inequality. So vectors which have positive scalar, positive product with the K, they are shifted, and negative, they do not shift. Then it is easy to check. Maybe I left the problem. That scalar product of EJ prime and EA prime is equal to BJI prime. So we just changed our basis. So and obtain the matrix B prime. So B and B prime are Gram matrices of the same scalar product, but in different bases. Therefore, they have the same rank. Okay. Any questions? Okay. I want to comment a bit on the proof of this theorem. I'm not going to give it in full detail, but I want to explain the idea of the proof. The proof is elementary, so it doesn't use any advanced, just the level of the basic course of the algebra. So the proof goes like this. First, first simplification is the following. So U of t is defined as intersection of the rings of Laurent polynomials on T and any adjacent clusters. So actually the intersection of n+1 rings of Laurent polynomials. First, one can show that it is actually sufficient to consider such intersection. So intersection of n rings where we have AG, both AG and EG prime, but no the inverses. So actually, this is some transformation which made look into one index. The second step, and which is actually most difficult step, it's of the same species, but here we replace two. Here the intersection goes from G of 2 to n. So we fix some index, say 1. And here A1 and A1 prime, AG and G prime. And for all other variables, we have Laurent polynomials. And the third step, so here AG2 prime is mu j mu1 aj. And here we have t. This is actually the last step. We have to show that if we have two seeds which are adjacent by some mutation, say in vertex number 1, two, then the corresponding this upper bounds isomorphic. We represent them in this form, and actually the only thing which one have to change is the terms which correspond to A1 and A2. For them are isomorphic. So here we have for T we have A1, A1 prime, A2, A2 prime, and for no, we have to for any J. So J is now for split here is 2, and so this term here which consists of A1, A1 prime, A2, A2 prime, and here A1 and A1 prime, A2, and here A2, 2 prime, 2 primes. Principle after the first notation, the form of A2 prime prime can be different. And one can actually show that these rings are isomorphic. So on the level, so idea of the proof is the following: that we reduce everything to consideration of 1 and 2 variables. And for 1 and 2 variables, everything can be computed, and we are done. Okay, I probably will write more details in notes, and maybe manage to prepare some problem from this proof, but this is what I wanted to say for the idea. Okay, questions? This is story for upper bound. One can ask, is there some sort of, one can hope that there is some sort of lower bound, and there is actually there is no very good lower bound, but naive lower bound can be defined similar to upper bound. So we want to bound the upper cluster algebra, and if we consider just the star of some seed, then we have to include all the cluster variables A's and cluster variable which are mutated. So A1 prime, A2 prime, and so on. And consider the corresponding rings. And of course, this ring is a subalgebra in the cluster algebra. Somehow looking, if you look here, so what we're doing is all this replacement, we replace terms like AG, say A1 plus powers plus minus 1 by A1 and A1 prime. And if we do this for all n's, we come to a lower bound. Okay, so obviously lower bound is subalgebra in the cluster algebra. Seed is acyclic if there is no oriented cycles in the corresponding QE. One can renumber vertices in a cyclic seed. Such that BAG is greater than 0 if I less than G. So all vertices are maybe no. Okay. Like this. Maybe no. If not, I cannot write if. Hence, so all vertices goes from all edges goes from the vertices with larger number to vertices with smaller number. Okay, and there is a theorem that the spirit of the previous theorem that T is acyclic, then actually the lower bound is isomorphic to upper bound. And for example, if seed is both acyclic and coprime, then all the bound are isomorphic to the cluster logic. There are some cases where this holds. So for example, a case which corresponds to Grassmannian, or better to say a fine cone of a Grassmannian, correspond to the quiver like this, just sequence, just AN quiver. And whatever orientation put here, this is a tree, so it will be the corresponding quiver will be acyclic, and there is no. It will be coprime. The adjusted matrix is drinking. Again, clearly there was no proportional rows in the. It has a cyclic, maybe better to write here full rank. The rank of the adjacency matrix the adjacency matrix will be like this. We have zeros, and here some numbers, here also some numbers, ones, so it has full rank. So, for example, for this case, which corresponds to Grassmannian 2n plus 3, the cluster algebra consistent with lower and upper cluster algebras. Another remark that if you have just two vertices, hence the seed is acyclic. And actually, this is what we somehow secretly used in the previous proof, where we reduce everything to two variables. So for two variables, we can replace A and A inverse by just A and A prime, and then the argument works. But we cannot write the we cannot write the similar formula where we have not two, where we replace the two variables, any three variables by the A and A prime. As I said, full rank condition is rather mild condition. Quite often we have full rank, or we can make a matrix to have full rank adding some frozen variables. So this is possible. But acyclic is contrary is quite rare. Usually quivers which we get from some natural manifolds like double Breuer cells, which we discussed last month, and actually we'll discuss in a minute today, or Grassmannians, or not like this 2n plus 3, but high Grassmannians, or spaces of local system. Usually such manifolds, squares for such manifolds will have oriented cycles. Okay. I suppose no questions. Now let me return to double Breuer cells. For double Breuer cells, correspondingly, I have also want to state the main theorem. the theorem is the following. So if we take some double brass cells, G of V, and consider the algebra on regular function of this, then this is actually isomorphic to upper cluster algebra for the quiver which we constructed in the previous lecture. In particular, it means that geometrically, it means that this double brass cell is the A cluster variety up to codimension 2. The ring of regular functions does not know nothing about codimension 2 submanifolds, codimension 2 submanifolds, but up to this, we know. Maybe I should try this. Well, then I forgot some letter. Okay, I have prepared here some example, but I didn't explain you example of what. So I'm not good. I will not give. I will say the right proof, but it will be proof with gaps. And here, I mean, I didn't prove previous theorem also, but actually today I plan to have 3 theorems. So first theorem was about upper cluster algebra and states that if seeds are coprimes, then this upper bounds for T and T prime are isomorphic. And actually I didn't prove it, but I use a scheme, and it is elementary and it is quite straightforward. The second theorem was about a cyclic case, and I think this proof was also elementary but longer, and this is why I omitted. And the theorem for double brass cells, it requires this proof is in principle also elementary, but not even, I think it's much more sophisticated. It requires some identities with minors, so I actually will not give it in full detail, but I want to explain the scheme of this proof. And first step, I want to state that that our CT is full rank. Let me recall how this seed looks like, how this corresponding quiver looks like. And this can be seen on the example. So for any unit V, we draw the network. So we pick some reduced decomposition of the element of the double while group. For reflections of with the bar, we draw vertical H with the black vertex on the up and white on the bottom. For the S, we draw vertical H of the opposite coloring. And in this way, we obtain some network, and the vertices which will correspond to faces of this network. And maybe I also should add one face upstairs. this here I draw all my faces, and maybe I also label them. So first I label them from the bottom to the top of this unbounded faces, A1, A2, and this A3. The face in the very bottom have no labels. The corresponding cluster variable is equal to 1. No story. And then I label faces by their left border. Sorry, by their left border. The vertical segment on the left of this face. So this face will have next number A4. Here, the face will have number A5, A6. Next will be this A7, A8, A9. This labeling by the left border somehow correspond to the labeling by the order, the reflections, the reduced decomposition. Anyway, so let me write it. Let us denote by A1. So now I'm going to explain why T has a full rank in this case. So let me introduce some notations that some number M capital is equal to len L of U plus some number, or I change my N capital is a number of bounded faces. Equivalent it is a number of, instead of number, I'll just write this. Equivalent is a number of unfrozen variables. Then we let us write A1, AN, or maybe let's be with the corresponding unfrozen variables. Labeled by their left border. So now in this example, maybe I move this example to the next page. In this example, we have, I believe, 4 unfrozen variables, 4 closed faces. So first of them will be 4, A4. Second will be 5. Third will be 6, and fourth will be 7. In this case, this is just something in the middle of the full list of variables. And let now with another bracket, A1, AN, left neighbors of for any closed closed face, we have its left neighbors. So in this case, A1 will be what we take face number 4, it takes its neighbor. So it is A2. A2 will be A1. A3 is left neighbor of A6, so it is A4. A4 is a left neighbor of A7, this is A6. And what do we see? Now I claim that adjacency between vertex number I in such brackets and such brackets is equal to plus minus 1, because the corresponding faces have one common edge, vertical edge. And B I J is equal to 0 if I less than G. This is because for the face which corresponds to this I, its right border is left border of the face with this J, because the right border of the I's curved face is the left border of the I's face in such bracket, but its left border is the left than the left border of the face number J. So here, for example, you see that face A2 have 0 adjacency with these 4 faces. Face A1 has 0 adjacency with these 4 faces. And last, A4 have 0 adjacency with this. Okay. Hence, the matrix, if we consider matrix B, which is n times m, it will has so the matrix, the minor B1 n 1, the submatrix will be low triangular. So we have plus minus 1s on the diagonal, 0 upper diagonal, and something here. Hence, rank of B will equal to. So B has a maximum rank. Hence, we can apply the corollary and see that upper cluster algebra is isomorphic to its upper bound. And this is actually only end of the step 1. Any questions? Okay. Now let me explain the step, at least what is step 2. And step 2 actually consists of 2 lemmas. Lemma 1 states the following. It has a lemma. Let me write 1 in this in such manner and a in such manner. First, that all these cluster variables regular functions on double cell and this is more or less obvious since they are minors and minus regular functions, and B, which is quite less obvious, that we have a map from C not equal to 0 of L of U plus L of V plus N to this double cell. Sorry, I want to write down map in opposite direction. We can take double cell and consider the map from this double cell to the set of non-zero complex numbers of the size length of U plus length of V plus N, which is given by G goes to the corresponding minors. Maybe it's better right here, not GUV, but U, which is subset of GUV, and U is a set of G such that all the corresponding minors non-zero. So for each phase, we just assign the minors. Maybe you remember, when you look at the zigzag path below the corresponding phase, and from this we can compute from this we take the number of rows and number of columns of the corresponding minor. So we have this map, and the claim of the lemma this map is biregular isomorphism. So the open subset, which is defined by the equations, all minors which correspond to unfrozen variables is all minors are non-zero, is isomorphic to C in this power. We know from that the dimension of the double cell is equal to this number. So we know that minors provide the coordinate system of this double cell. But this is a more difficult statement because they provide coordinate system, but we do not sure that this is very regular map. Maybe we should, I don't know, exclude something more. Okay, so this is lemma 1, and more difficult, there's a similar lemma 2, which states that for any G, we take mutation T to TG, mutation G, and we have A, that our new variable AG, okay, AG maybe without brackets, AG prime is also regular on GUV, and statement similar to B holds. So if we define QG as a set of G from the double cell such that delta I of G not equal to 0 for I not equal to G, and functions which correspond to G prime. Okay. Then there is the map from G to C to the power of is also by regular isomorphism. And even step A now is absolutely non-clear. So we know that quite often mutations is given by some identity on determinants and minors, and this new variable is also minor, but not always. And if it is not minor, then it is completely unclear why it is a regular function on the double Brière cell, because it will have some numerators, and so what? Why it is non-zero? Why it is have no poles on the full double Brière cell? Okay, so this is some theorem which is proved by Zelinsky, and now finally how to use it. And these two lemmas are used as follows. And I'm now finished the proof, and the argument is actually of the same type as we will see next time in the proof of starfish lemma. We take U. Okay, let me call this step 3. We take U, which U union of this. This is some each uj and u are open subset in double Brière cell. It is defined by some inequality that some function is not equal to 0. And we claim that codimension of U and GUV is at least 2. Why it is important? Because if you know this, then regular functions on U are the same as regular function of the double Brière cell. But regular function on U, this is exactly this upper bound. Because you see regular function on each of this on this regional space U, the Laurent polynomials on the original cluster variables, and on each of this Uj, the Laurent polynomials on the seed, which is given obtained from original by one mutation. So we are done. We proved the regular function, and by as was explained above. In the step 1, T is a full rank. So this U is the upper cluster algebra. So this is why this claim is important, and why is it true? Because what does it mean that point belongs to the complement of this open subset? It means that it means that it does satisfy how to say so. So complement of the U is a points where at least of one of the cluster functions is equal to 0. And here we take some such complement that in order to belong to the complement of all this, two cluster functions should equal to 0. So this is why we have a co-dimension at least. Okay, so it's a long proof. Let me draw the square and ask for questions if there are any. I will write it more clearly in notes. I apologize, maybe I'm too vague. And I give references, and here are the references. Cluster algebra 3 by Bershtein family. And in this paper, they introduced notion of upper cluster algebra. They proved the theorem which I gave it in the very beginning, and they applied to double Russell. So all the three theorems which I stated today, and actually many other, there are a lot of other results are proven in this beautiful paper. Let me end with a few remarks. Maybe not remark, as a fact. Actually, it is proven later, 7 years ago, that upper cluster algebra for double Russell upper cluster algebra is isomorphic to original cluster algebra, standard cluster algebra. So this theorem says it's cluster algebra, just cluster algebra is isomorphic to the Riemann functions on the double Russell. There is an example where such isomorphism is not true. Example. And the example is given by this quiver, which is sometimes called Markov quiver. So it has three vertices, which each of them are connected by two arrows. And so for this quiver, A is not equal to A bar. So one can construct a functional Laurent polynomial, which will be Laurent polynomial in any seat. In this case, the corresponding seat is coprime, and all seats which are obtained from this one are also coprime. So this is not full rank case, but coprime. So the upper algebra is isomorphic to its upper bound, but one can construct the Laurent polynomial which don't belong to cluster algebra. And so this simple example, and I'm going to give a problem. Maybe this will be a problem. And another remark which I'm going to give, and maybe I'll apply to some problem, is the following. So we can take the particular case of double Breuil name is the following: GW0E. So when one of the elements of the while group is the longest element, and another is just identity. So then by definition, this will be BW0B intersection with B minus E B minus. So the second set is just B minus, and the first set is more or less the same as G. So this intersection is just B minus. So cluster structure on the B minus. So a cluster structure on the double Breuil is actually gives us a cluster structure on the Borel subgroup. So B minus has cluster structure. But there is also a way to go to even further from Borel subgroup to nilpotent subgroup. Namely, N minus is a B minus quotient by the Cartan. And in terms of the quiver, it means that we are just erase frozen variables from the one side. So if we take our E, you remember we take some H, E, E. So we just erase first H's. And hence we get the cluster structure on N minus. And this is rather famous example. So this was the spirit of the double. So we constructed the, okay, so this, I don't know how to comment. So it has a lot of meaning in terms of representation theory, and actually original constructions, original conjectures about relation of cluster algebras and so-called canonical basis were stated about this nilpotent subgroup. And what I want to say is that this is just a particular case of the construction for the Breuil. Maybe I already said that, but maybe once again, let me say that remark that GW0W0 is the open subset in G. So we have not precisely cluster structure in G, but cluster structure in open subset of G. Okay. I think it's time to stop. Are there any questions? Okay, if no question,